For this example, we're going to let the vector space in question be the set of 2 by 2 matrices. I will pose the following question. Why are each of the following sets not bases of the set of 2 by 2 matrices? So first and foremost, let's give ourselves a little reminder that the dimension of the set of 2 by 2 matrices is equal to the number of entries that we have in a 2 by 2 matrix, which would be a total of 4. So when we take a look at part A, which contains these 5 2 by 2 matrices, it is readily apparent to us why this is not going to be a basis. So because the dimension of our vector space is equal to 4, and S contains 5 vectors, we need these two numbers to be exactly the same in order for it to be in order to be even eligible to be a basis. If you have too many vectors, S is guaranteed to be linearly dependent. Which means that one of these 2 by 2 matrices can be expressed as a linear combination of the others in the set. That means that at least one of these matrices can be expressed as a linear combination of the others in the set. Now, if you wanted to, you could set up a system of equations to determine which one of these can be expressed as a linear combination of the others. Moving on to part B, we have the following matrices: 1, 2, 2, 3, 0, 1, 1, 0, 5, 1, negative 1, 4. Now, once again, the dimension of the vector space that we're dealing with is 4, but we only have 3 vectors within the set. So we'll point out that because the dimension of the vector space in question, because the dimension of V is equal to 4, and S contains 3 vectors, it is guaranteed to be not a basis, because a set of 3 vectors cannot span a 4-dimensional space. S will not span V. So that's guaranteed. Now, the potential exists it could also be linearly dependent, but that really doesn't matter to us because we've already got our one condition that we need to verify that it's not a basis. Now, continuing on to part C. In part C, we have the following set of 4 vectors. We have 2, 1, negative 1, 2. We have 3, 6, 7, 4, 0, 4, 2, negative 1, and negative 4, negative 2, 2, negative 4. So allegedly this is not a basis, but it's not because of the number of vectors within the set. So what I'm going to point out is we could refer to these 4 vectors as vector v1, vector v2, vector v3, and vector v4. The thing that I'd like to point out is the relationship that you may have already noticed between v1 and v4. So the thing to take note of is that if I were to take negative 2 times v1, I would get exactly v4, which means that we have a non-trivial solution of a linear combination of these vectors being equal to the 0 vector. So we could take 2v1 plus 0v2 plus 0v3 plus v4, and we would get the 0 vector in the set of 2 by 2 matrices. As such, this set of vectors is linearly dependent. Therefore, S is linearly dependent. Now, the other thing that this means is that it definitely won't span the set of 2 by 2 matrices, but we don't really need that at this point. Now, with that in mind, we do have a slightly more complicated example in the following form. So here is once again a set of 4 vectors, S being 1, 0, 1, 2, 2, 1, 2, 1, 3, 2, 4, 0, and 3, negative 1, 0, 5. The question is this a basis? Well, the directions sort of imply that the answer is no, but let's set up why not. Now, for this one, it's a little less obvious what's going on due to the fact that one of these isn't a multiple of the others. So what we're going to try to do is see if we can express one of them as a linear combination of the others in the set. So we'll set up C1V1 is equal to, plus C2V2 plus C3V3 plus C4V4 is equal to the 0 vector. Now, if we were to compare the 1-1 entries, this would mean, let's just go ahead and copy these down. 1, 0, 1, 2. C2 times 2, 1, 2, 1. C3 times 3, 2, 4, 0. And C4 times 3, negative 1, 0, 5. That's going to be equal to the 0 vector and the set of 2 by 2 matrices. Oh, excuse me. Thank you. So, with those things in mind, let's set up a system of equations. Excuse me. Oh my gosh. Gotta knock that off. Where we will compare the 1-1 entry, the 1-2 entry, 1, 2, 2-1 entry, and 2-2 entry, and we'll look at the coefficients of C1, C2, C3, and C4. So 1-1 entry for C1 is 1, 1-2 entry is 0, 2-1 entry is 1, and 2-2 entry is 2. Doing the same thing for each of these matrices, it'll look sort of like what we would do for vectors in R4. Negative 1, 0, 5. And we augment with the 0 matrix. Now I'm interested in taking this down to reduced row echelon form, and in order to do so, I am going to grab my handy dandy graphing calculator that for some reason is with me at all times. Heading over to the matrix menu, we'll enter this 4x5 matrix. 1, 2, 3, 3, 0 for the first row. 0, 1, 2, negative 1, 0 for the second row. 1, 2, 4, 0, 0 for the third row. 2, 1, 0, 5, 0 for the fourth row. Let's go ahead and make sure that everything got inputted correctly. First row is good, second row is good, third row is good, fourth row is good. Good. So, entering the matrix menu, we'll take this down to reduced row echelon form. Re-enter the matrix menu, select our matrix, and hit enter. Well, I'll be. I guess that we do have a linearly independent set here. So in reduced row echelon form, we see the identity matrix augmented by the 0 vector. Now, we have a theorem that states that when you have the magic number of vectors, that we are dealing with something that is both linearly independent and spanning. Therefore, what we can assume is that S is a basis of V. So, twist ending there for us.